So this would be the last lecture of electrostatics, and after this the domain of capacitors would start. And I have a little bit of request. Okay, see, you might develop certain doubt after some questions. Okay, follow through the end of the lecture for resolution of this doubt. Okay, see, I'm spoon feeding you irodov. Okay, it's not like question answer. No, the concepts are given, the fundamental discussions are done. So if you want to ask doubt, make sure you have seen till the end of the video. Okay, that's my only request out here. Understood? In this question, the electric field is given by E is equals to AYI plus AXJ, isn't it? This is the electric field. Now I have already said you a different two sets of formula. So whenever potential is given, okay, electric field is equals to minus dV by dxi minus dV by dyj minus dV by dz. Okay, and whenever electric field is given, dV or minus dV is equals to Ex dx plus Ey dy and Ez dz. It means x component of electric field, Ey is y component of electric field, and Z is Z component of electric field. So out here, when the electric field is given by AYI, I'm just multiplying the scalar here with the inside the bracket, plus AXJ. What is x component of electric field? This one. Anything associated with I is nothing but x component of electric field, and anything associated with J is nothing but y component of electric field. So if I want to find out the potential, I have to use this formula. Okay, so minus dV is equals to Ex dx or Ay into dx plus Ax into or Ey into dy. Okay, when I integrate this, what will come out here? Minus dV is equals to, if I integrate this one, Ay into x, Ay into x. Out here, Ay is treated as constant, or anything apart from x. Out here, anything apart from x is treated as constant. Out here, anything apart from y is treated as constant. So out here, if I integrate this, it would be Ayx plus Ayx plus some constant. Okay, now whenever you have similar kind of variables, see, your basic intuition out here would be Ayx plus Ayx is equals to 2Ayx, but that is not the correct way. Okay, whenever you have similar kind of variables, group them together. That means group together similar kind of variables. Okay, similar type of variables. That means what? That means this Ayx would only be written only once. So if I integrate this one, it would be minus V, okay, is equals to Ayx plus some constant. Okay, see, and why did I do that? Whenever I integrate, okay, whenever I integrate electric field, okay, what should come out? Potential should come out. So if I differentiate this potential, the same electric field would come out, no? So if you differentiate this function, you get the same thing as this one. Okay, but if you do a mistake, or if you do a mistake of putting Axy plus Axy is equals to 2Xy, if you do 2Xy plus some constant out here, and when you differentiate this V with respect to X, and when you differentiate that formula for potential in this formula, the electric field out here would not come same as this electric field. Okay, so whenever you're integrating for electric field, no, always make sure that similar kind of variables are grouped together. Okay, on this question, okay, that to do the same thing, this is x component of electric field, where this is y component of electric field. Now if I apply the formula, minus dv is equals to ex dx or 2a xy into dx plus ax square minus ay square into dy. Now if I integrate this one, okay, or minus v is equals to, what happened out here, minus v is equals to 2a y x square by 2, isn't it? See, 2ay is constant and x dx is nothing but x square by 2 plus ax square y minus a y cube by 3 or a y cube by 3. If I integrate this one, I'll get these two terms. Fair and fine. Plus some constant. Okay. Now if I multiply negative on both hand side, I'll get minus. See, these two and these two get cancelled. Okay. So it will be nothing but minus a y x square minus a y x square. See, I just rearrange this term out here. Minus a x square y minus a y x square minus a y plus a y cube by 3 plus some constant. Okay. Now the primary intuition you might have is minus 2ay x square minus 2ay x square can be is equals to minus 2ay x square, but that would be wrong. Okay. So whenever you have similar type of variables, group them together. So note, okay, always group together similar types of variable. So group together similar types of variables. What I mean by that is, see, these two or v would be equals to minus ay x square. That means if this variable is there two times, I'll just write it one time only. Okay, plus a y cube by 3 plus some constant. Okay, now you might have the question, sir, why are you doing like this? Why isn't minus a y x square minus a y x square is equals to minus 2ay x square? See, so I'll do the wrong approach first, or I'll do the wrong approach, then explain you what's going wrong. Wrong approach. Okay, so if I do v is equals to minus 2ay x square plus ay cube by 3 plus some constant. So I'll explain to you why this is the wrong approach. See, if I differentiate this term, that means electric field is equals to minus dv by dx I minus dv by dy j minus dv by dz k. So if I apply the formula out here, electric field is equals to minus d. What is the value of v? See, the value of v is this entire term, no? So when I differentiate this entire term with respect to x, what do I get? I'll get something like minus 2ay into 2x plus 0, isn't it? I cap. Now if I differentiate this entire term with respect to y, what do I get? Minus 2ax square y into 3ay square by 3j or j cap, isn't it? Now see, the electric field will come out to be 4 or a yxi plus 2ax square plus or this 3 and this 3 would get cancelled and it will become plus ay square j cap. See, now is this electric field and this electric field the same thing? No. Out here see it is 2axy and out here 4ayx is coming out here. Understood? So this approach would be wrong. But when you differentiate this potential with respect to x and y, you would get the same electric field as this one. Let's apply the same formula out here. So electric field is equals to minus dv by dx. So I'll differentiate this entire term with respect to x. It is nothing but minus ay into 2x I minus dv by dy. So I'll differentiate this entire term with respect to y minus a x square y plus 3ay square by 3j. Okay, so it would be electric field is nothing but 2ayxi minus or minus ax square, 3 and 3 would get cancelled, it would become ay square. Okay, ax square plus ay square j. If I multiply minus inside the bracket, I would get this to be plus, this to be minus, and out here it would be plus. So it would be something like this. So electric field would be equals to 2ayx I cap plus ax square minus ay square. Now this electric field has the same value of this electric field. Understood? So whenever you are integrating electric field, or whenever you are integrating potential from electric field, whenever you find out the same type of variables, instead of adding them, write them only once. Is that understood? Okay. If you add them, the electric field, that would be the wrong approach. You'll get the wrong potential. Okay. Now on this question, this is x component of electric field, this is y component of electric field, and this is z component of electric field. So potential, or minus dv, is equals to ay dx, okay, plus ax plus bz into dy plus by into dz. And when I differentiate this, or when I integrate this, minus v is equals to ayx plus axy plus bzy plus byz. Now this term and this term are the same thing. Okay, so I'll write them only once. This term and this term are the same thing. Okay, plus some constant. So my potential would be minus v is equals to ayx plus bzy plus some constant. Okay, or v is equals to minus ayx minus bzy minus some constant. Okay, so whenever you have integration or partial integration, okay, if you find same type of variable, write them only once instead of adding them. Okay, same type of variable should be written only once. That is the main concept out here. Okay, now in this question the potential is given by minus ax cube plus b. Okay, we have to find out the charge distribution. So how do we approach this kind of problem? The first intuition is we have to find out the electric field. Okay, and after finding out the electric field, the next process would be apply Gauss law, where Gauss theorem states that electric field is equals to E dot A is equals to Q in by epsilon naught. And from here I'll find out the charge distribution. So I have a faint intuition of how I'm about to solve this problem. So let me first find out the electric field, isn't it? So electric field is equals to, let's say electric field is equals to minus dv by dr. Okay, or if r can be written as xi cap plus yj cap plus zk cap, it is nothing but dv by dx I minus dv by dy j minus dv by dz k, isn't it? I have already taught you this one. Okay, so electric field out here is nothing but minus d into minus ax cube plus b by dxi, isn't it? Minus dx cube plus b by dyj minus dx cube plus b by dz. Okay. Now if I see the equation of potential, it has no y and z terms. So out here the electric field in y component would be 0 and z component would be 0, because everything is constant out here, no? Isn't it? So our electric field is in the direction of x direction, which is equals to minus, I have to differentiate this term with respect to x. So when I do that, I'll get minus 3ax square, okay, I cap, or electric field is equals to 3ax square I cap. Now from this question, I get two hints, or from this electric field, I get two hints. The first hint is the electric field is only in x direction. See, there exists no component of y or j. Okay, and as I'm increasing the value of x, what is happening? the value of field is increasing, isn't it? So electric field would be somewhat in x direction. So if I draw a coordinate system, okay, y-axis, x-axis, and z-axis is towards yourself. So electric field will be only in this direction, no? Okay. As I'm going further down the axis, the magnitude of electric field would increase. That means the density of electric field lines would increase. But one thing to note out here, there exists no component of y component of electric field or z component of electric field. Okay. As I'm moving towards right, the density of electric field is increasing. That means the gap between electric field is decreasing and decreasing. Okay. That means what? As I'm going towards right, the charge that is kept in the space is increasing. Okay. So at any point, okay, so from this kind of electric field distribution, you get the idea that we have to take an elemental surface area out here. Okay, this surface area can be of any shape. One thing to note out here is, although I'm taking the elemental surface area out here, okay, doesn't mean that the charge exists only in this or only in this confined space or only in this confined area. The charge exists throughout the y, from y is equals to infinity to minus y is equals to minus infinity. Okay, from z is equals to plus infinity to z equals to minus infinity. To avoid kind of taking bigger area, I just take an elemental area. So the elemental area that will behave out here will be same as infinite area. For example, what I'm trying to say is, for infinite plate, okay, how did the electric field look like? This one, like this. So did you take an entire area Gaussian surface to calculate electric field? No, you just took an elemental area, no? And then you took an Gaussian surface area out here. You took an Gaussian surface area out here, and then you calculated the flux. The same type of thing I'm doing out here. Okay. Although the charge exists for infinity, okay, although the charge exists infinitely, I'm just taking an elemental area. Okay, I'll just be calculating the electric field due to this much charge, because there is no y component or z component of electric field. Okay, so let me erase this one. So my domain of calculation, or the area I'm going to calculate, is only this much. Okay, is only this much. That is my domain of calculation. Okay, so if I find out what is happening inside this domain, I can find out what is happening in the entire space, because the electric field, see, electric field from outside won't be coming inside this domain, isn't it? So I do not need to take this area. Okay, so let me consider an elemental charge or elemental length out here. Okay, of length dx or of thickness dx at distance x from the origin. Fair and fine. This is an elemental disk of thickness dx. Okay, now this elemental disk contains dq amount of charge. Okay, and if I find out the electric field due to this much element of charge, okay, I can simply extrapolate what is happening or how is the charge distribution for this entire space. Okay, so for this elemental charge, okay, I have to find out the electric field. Okay, so I can easily draw a Gaussian surface. So how would my Gaussian surface look like? The Gaussian surface would be nothing but out here and out here. Okay, similar to what you did for flat plates or infinitely flat plates. Okay, so say for this much amount of charge, okay, I took an Gaussian surface out here only. Okay, see, the Gaussian surface should be out here only. Okay, just for the sake of simplification, I drew this surface area out here. Okay, this is my Gaussian surface. Okay, and this Gaussian surface is situated out here only, just outside the or just attached to the this surface of the charge. Okay, so what is the electric field out here? The electric field out here is nothing but 3ax square, isn't it? Remember, this Gaussian surface is attached to this surface. just to avoid clutter, I have just drawn this separately, this surface and outer separately. Okay, this Gaussian surface is attached to the charged or elemental charge. Understood? Okay. So the electric field through this Gaussian surface is 3x square. That much I have known. Now can I apply Gauss law? Where Gauss theorem states that electric field into Gaussian area is equals to Q inside by epsilon naught. Okay. What is the value of electric field? 3ax square. Okay. What is the value of Gaussian surface or Gaussian area? Let this area be A. Okay. So let the area be A variable. What is Q inside? Q inside this Gaussian surface is nothing but this much of elemental charge, or dq. Dq is nothing but volumetric charge density into volume. And what is the volume of this elemental disk? The area into thickness. So Q inside is nothing but volumetric charge density into this area into thickness. Area into thickness is nothing but volume. So A into dx. Okay. So if I take these two equation, if I solve for these two equation, what would I get is 3ax square into A is equals to rho A dx by epsilon naught, isn't it? A and A would get cancelled. Okay. So I'm left with equation 3ax square is equals to rho dx by epsilon naught. Okay. And what do I have to find out? I have to find out the value of rho. Okay. Now one thing, most of you might have the intuition of let's take x square down out here and integrate it. Okay, x to the power minus 1 and it will be fair and fine. But one thing you need to remember out here, this volumetric charge density is a function of x. No, see, this volumetric charge density is a function of x. Okay, so when I'm integrating, this entire thing is a single factor. Okay, you cannot separate this. So what I have to do out here, in the left hand side, okay, I have to make a component of dx and cancel out dx out here and dx out here, similar to what I did with area. Okay, so x square, if I differentiate x square, what do I get? Dx square by dx, what do I get? I get 2x, or x square can be written as 2x dx, no? See, okay, so this x square can be written as 2x dx. And now I can cancel out this dx and dx. Okay, so 3a into 2x dx is equals to rho x dx by epsilon naught. Okay, dx and dx would get cancelled, or 6ax epsilon naught is equals to charge density. One more thing, most of you have got stuck out here. Why didn't I integrate by putting x squared down out here? See one thing, this charge density or volumetric charge density is a function of x. Okay, so you cannot separate in mathematics. In the topic of integral, you cannot separate when some function is there or some function is integrated with respect to x. Okay, understood? Or if this charge density was given, already given, as if suppose this charge density was given 6ax square epsilon naught, already given, then what you could do is you could bring this x square down out here, calculate this one and this one, and then integrate whatever dx is given or whatever integral is there with dx. Okay, but in case a function is there somewhat like this, you have to cancel out the dx, or dx is cancelled out using this method. Okay, this is a topic of mathematics. So in this question there are two infinite plates. Okay, one is of positive charge, one of the plate is positively charged and the other plate is negatively charged. Okay, let's say positive charge density sigma and negative charge density minus sigma. The distance between the plate is d. Okay, before we go further into the question, what is the electric field inside the plate? The electric field inside the plate goes from positive to negative. okay, and the electric field is equals to, or inside the plate is equals to sigma by epsilon naught. I have already said that before. Understood? Now, if I consider the datum line to be at the center of the plate, okay, what is the potential difference between this point and this point? Okay, or what is the work done in by electrostatic force in bringing a positive 1 coulomb from this point to this point? It is nothing but force into displacement, or sigma by epsilon naught into d. So the potential difference, okay, is equals to sigma d by epsilon naught. So the potential difference between the plate is given by sigma d by epsilon naught. Now some of you might say, sir, it is minus sigma d by epsilon naught. It doesn't make a difference. Okay, if you take this final as this as initial, it will be minus sigma d by epsilon naught. If you take this as final potential and this as initial potential, it would be sigma d by epsilon naught. That means if you take the positive 1 coulomb charge from out here to out here, potential difference would be this much. If you take the positive 1 coulomb from out here to out here, the potential difference would be this much. All you have to remember is this is the higher potential, this is the lower potential. Okay. Now, what is the electric field at the negative plate? The electric field at the negative plate is same, sigma by epsilon naught in this direction. Okay. Similarly, what is the electric field at positive plate? The electric field at positive plate is also sigma by epsilon naught, isn't it? In this direction, sigma by epsilon naught. So this much is given in the question. Not given in the question. This much you already know. Okay. Now in the question is what is given is, see, let me erase this central line. Okay, a new charge is introduced. A new charge is introduced. Okay, inside the infinite plate. The charge density of this new charge is rho. Okay, and due to this new charge, the electric field at one of the plate will become zero. Okay, so what is happening out here is new charge is introduced out here. Okay, this is the new charge. The thickness of the charge is d. Okay, see, due to this electric field at this point would be in this direction, electric field at this point would be in this direction. So if I arrange this one out here, the electric field to this positive charge on the positive plate would be towards left. The electric field due to this volumetric charge on the negative plate would be towards right, isn't it? Electric field is towards right. Okay, this point and this point are at the same point. Understood? Now the question is saying the net electric field at one of the plate will become zero. So can you guess which plate is it? Obviously the positive plate, isn't it? Out here both the electric fields are added. Out here the electric fields are subtractive in nature. So the electric field at positive plate is equals to zero, or the net electric field at positive plate is equals to zero. So can you guess the magnitude of this electric field if the net electric field at the positive plate is equals to zero? Obviously this magnitude of electric field is equals to sigma by epsilon naught. Understood? Then only it will become zero, no? Okay, E is equals to sigma by epsilon naught. Okay, and one more thing. Instead of giving potential difference as delta V, they have used delta psi. Okay, so instead of using delta V, I'll use delta psi. I'll use the same variable as erodov. But it's not advisable to use the same variable as erodov. Okay, because most of your JE question they'll use NCRT notations. Okay, fair and fine. Now I have found out the electric field. What the question is asking is find out the charge distribution rho, or find out the charge density rho. Okay, so I have to use Gauss law, where electric flux is equals to electric field into area is equals to Q inside by epsilon naught. So I have to take a Gaussian surface out here. So the Gaussian surface would be, see, I'm normally taking a cylinder, but can be any area. Okay, a square area also, a rectangular area also, it doesn't make a difference. Okay, because ultimately the area would get cancelled out. Okay, so what is electric field? The electric field is given by sigma by epsilon naught. Okay, the Gaussian surface, okay, the Gaussian surface is nothing but A plus A, which is equals to 2A. The Gaussian surface is equals to 2A. What is charge inside? Charge inside the Gaussian volume is nothing but charge density into this volume, okay, or charge density into volume. Volume is nothing but A into D, isn't it? Volume of this entire cylinder is nothing but A into D. So A into D. Now if I take these two equations, okay, sigma by epsilon naught into 2A, I'm taking these two equations, okay, is equals to rho A D by epsilon naught. Epsilon naught would get cancelled. A and A would get cancelled. So rho is equals to 2 sigma by D is equals to rho. Fair and fine. I have already obtained the answer. Now the problem is in the question they have mentioned nothing about the charge density sigma. Okay, they have only given this charge or this potential difference is equals to delta V or delta psi. Okay, and find out the charge density rho. So obviously I have to eliminate this sigma. Understood? There is nothing mentioned about the sigma, no? So from this equation, okay, what is the value of sigma? If I say potential difference is equals to sigma d by epsilon naught, okay, what is the value of sigma? The value of sigma is nothing but delta pi into epsilon naught by d is equals to sigma. And if I substitute the value of sigma out here, what do I get? I get 2 into delta psi by epsilon naught, sorry, by d square is equals to rho, or charge density is equals to 2 into delta V into epsilon naught by d square. Understood? This d and this d gets multiplied to become d square. So this was the question. The next part of the question is asking what is the electric field at other plate. The net electric field is at other plate is nothing but E plus sigma by epsilon naught, and the value of E itself is sigma by epsilon naught. So the net electric field at the other plate is E net is equals to 2 into sigma by epsilon naught. Problem is instead of writing the electric field in terms of sigma, I have to write the electric field in terms of rho. So what is the relation between sigma and rho? So sigma is equals to, or 2 sigma by d is equals to rho. So from this equation, can I say sigma is equals to rho d by 2? Okay, if I apply sigma is equals to rho into d by 2, I'll get electric field on the other plate is equals to this 2 and this 2 get cancelled is equals to sigma d by epsilon naught. Fair and fine. In this question, okay, potential is given by AR square plus V. We have to find out the charge distribution. So we have done this kind of question before, but the approach was we first have to find out the electric field, then you have to use Gauss law, isn't it? That was the approach. The approach would be same out here, okay? But in the previous approach, the potential was given in terms of x, y, and z. Out here it is given in terms of r, okay? R is nothing but a radial vector. Radial vector means, suppose this is the coordinate system. R means nothing but a radial vector. Okay, R. That means if you draw a sphere, okay, draw a sphere. R can be any vector, okay, of any vector pointing towards any point in the sphere where the magnitude of radius is nothing but given by R. Understood? That is what is known as radial vector. R vector is nothing but xi cap plus yj cap plus zk cap. But the magnitude of R is nothing but x square plus y square plus z square. That is the relation between radial vector and x, means Cartesian coordinate. This much is understood. So similarly, potential is given by AR square plus D. So electric field will be given by minus dV by dr, and the direction of electric field will depend upon the direction in which r vector is there. That means if I am finding out the electric field out here, okay, the direction of electric field will be in this direction along r vector. If I'm finding out electric field out here, the direction of r vector will be along this direction. If I'm finding out electric field out here, the direction of electric field will be in this direction, isn't it? So along the unit of r vector. So you all understood the concept of r vector, or electric field is equals to minus what is the potential, ar square plus v by dr, isn't it? Or electric field is equals to into unit of r vector. This unit of r vector just determines the direction of the electric field. Okay, or electric field is equals to minus a into 2r. Okay, yeah, into r cap, or electric field is equals to minus 2a r into r cap. Fair and fine. So we found out the value of electric field. Now what do you have to do? You have to apply Gauss law. Okay. Okay. Now to apply Gauss law, we first have to take an elemental charge. And how does elemental charge look like for a spherical charge distribution? Obviously a shell. Okay. If we integrate a shell from 0 to r, it will become a sphere. So let's take an elemental shell of radius r, or radius r, and thickness dr. Okay. The thickness of this sphere is dr. The thickness of this sphere is dr, isn't it? Now charge contained inside this sphere will give us the value of electric field, isn't it? So if I calculate the electric field out here, the value of electric field is given by minus 2 ar. Okay, that means the electric field will be in negative direction, but that's another question. Okay, that means the charge distribution will be negative, but the answer will give us all those terms. You do not need to worry about those things now. Okay, so I have to apply Gauss theorem from out here, where Gauss theorem says that electric flux is equals to electric field minus 2ar into what is the Gaussian surface out here. Gaussian surface is nothing but the outer surface of the shell. Okay, but the electric field is calculated, which is nothing but 4 pi r square. What is the surface area of a shell? 4 pi r square is same as surface area of a sphere, is equals to how much? Q inside. Q inside by epsilon naught. Okay, this is nothing but electric field. This is nothing but Gaussian surface area. Okay, but charge inside. Charge inside is nothing but volumetric charge density as a function of r into volume. And what is the volume of this shell? Surface area into thickness. So 4 pi r square. 4 pi r square is the surface area of the shell into dr, which is the thickness of the shell. Okay, this is volume. Volume is nothing but surface area into thickness. Understood? Where Gauss law states that net electric flux is equals to electric field into Gaussian area is equals to charge inside by epsilon naught. Charge inside is given by volumetric charge density into volume, where volume of this elemental shell is nothing but surface area of the shell into thickness. Okay, now if I solve these two, okay, minus 2ar into 4 pi r square is equals to rho r 4 pi r square into dr by epsilon naught. Okay, now I cannot simply manipulate the r square or r out here. Okay, first I have to take care of this dr. Okay, because rho r dr, that means this density is a function of dr, isn't it? So somehow on the left hand side also I must construct a term of dr. Now if you see this one, r square into r is nothing but r cube. So it is nothing but minus 8a pi r cube. See, 4 2 is 8, a pi r into r square is nothing but r cube is equals to rho r into 4 pi r square dr by epsilon naught, isn't it? Now 3r or r cube, if I differentiate r cube with respect to dr, I'll get around 3r square, or I can simply say that r cube can be written as 3r square dr, isn't it? So this can be written as minus 8a pi, and r cube can be written as 3r square dr, isn't it? Which is equals to sig or rho r 4 pi r square dr by epsilon. Now I can cancel out the left hand side and right hand side. Dr would get cancelled. Pi, pi, 4, 2 is 8. Okay. And what is left? R square. R square is getting cancelled. Okay. So sigma is equals to, sorry, rho is equals to how much? 3 into 2. See, let's calculate what got cancelled. Okay. This is replaced by 2. Pi got cancelled from both sides. 4 also got cancelled. R square and r square got cancelled. Okay, dr and dr got cancelled. So we are left with minus 6a is equals to rho r by epsilon naught. Okay, or rho r is equals to minus 6a epsilon. Okay, so out here we are ending with electrostatics. From next part of electrodynamics, okay, we'll just start introducing capacitor, not capacitor, how a charge introduced, or means we'll enter the domain of capacitors. Okay, now I have a doubt out here. Okay, sir, why aren't you cancelling out this r cube and r square and just taking this r down out here? Okay, so I'll do a wrong method out here. Wrong method. Okay, I'll just explain how this method is wrong. So minus 8a pi r cube is equals to rho x 4 pi r cube dr by epsilon naught. So r square. It was r square, no? It's out here. R square. So r square and r would get cancelled. So the remaining 4 pi, this 2 would get cancelled. Okay, or it would be minus 2a epsilon naught r is equals to rho x dr. Okay, and now you can, or now let's do it. 2a epsilon naught is equals to rho x dr by r. Sir, why aren't you doing by this method? How is this method wrong? Okay, why aren't you cancelling this and this at the beginning? And why are you doing it this in this method? Where, okay, let's see the right method, okay, by which I did the question. So out here minus 8a pi r cube is equals to rho x into 4 pi r square dr by epsilon naught. What did I say? I have to convert this r cube into a parameter of dr. I have to cancel out the dr and dr. So what did I do? I did r cube, or dr cube by dr is equals to 3r square, or r cube can be written as 3r square dr. Okay, and I made r cube is equals to 3r square dr. Then I cancel out the dr and everything out here. Sir, how is this a method? Okay, see, I explained it in a very simplified way. What I'm actually doing out here is, see, when I have this function, okay, so let this function be gx, and let this function be fx. Okay, fx. Now if I simplify the method, okay, gx is equals to fx dx, okay, by epsilon naught. You can shift around the epsilon naught as per your convenience. Okay, now which seems to be a more suitable method? Okay, this one, or cancel out the gx. That means what I'm trying to do is epsilon naught or 1 is equals to fx by gx into dx. Why epsilon naught? Okay, that means this method is equivalent to this method what I'm doing out here, isn't it? I just simplified it, and whatever is remaining with x, I integrate the variable with dx. Okay, or this one, the right way. Okay, correct way. D of gx, that means I'm differentiating both the term. D of gx with respect to x is equals to d of fx dx with respect to dx. Okay, now when I differentiate an integral with respect to dx, this term would come as how much? F of x, isn't it? And this term would come as d of gx with respect to dx. So which method is correct? This method is correct, no? This is the exact same thing I have done out here. Okay, just explained in a little bit layman's way. In a layman's way, what I'm trying to say is, if you differentiate this entire term with respect to r, and if you differentiate the right hand side with respect to r, we'll get the same equation as I have obtained out here. Check, do it once. Okay, differentiate this entire term with respect to r, differentiate this entire term with respect to r. So when you differentiate this term, this dx and this dx will get cancelled. Will be remaining with fx, and out here you just differentiate gx with respect to x. So this is actually what I have done out here. Understood? And this is the wrong way. Okay,